Welcome back, everyone. Today we're working on Nelson Math, Chapter 1, Section 2, Relationship Rules for Patterns. We're building on what we learned on in Section 1 from Chapter 1. So I'm going to be now getting into a little bit more depth into some of the terms I used yesterday. Here's a recursive pattern rule. A pattern rule that tells you the start number of a pattern and how the pattern continues. So start at 5 and add 3. That means, as it implies, start at 5 and add 3 every time. For this to work, for the recursive pattern to work, you need to know the previous number. So right now we have 4. Now that I have 4 term numbers, I can find out the 5th one and then the 6th one. As it stands right now, I can't find the 20th one, for example, until I find the 19th. And I can't find the 19th until I find the 18th. So you can see that while very easy to use, they have their drawbacks. That's why we have something known as the explicit pattern rule. This is a pattern rule that uses the term number to determine a term in the pattern. For example, I'm going to give you an instant of where we could do the term number multiplied by 4. So total number of legs on, in this case, let's say 6 chairs. So if I have 6 chairs, I don't have to find out how many legs are on 5 chairs, and then before that 4 chairs, and then 3 chairs. I don't have to do that. Nor do I have to say, well, 1 chair has 4 legs, 2 chairs have 8 legs, 3 chairs have 12 legs. That's a recursive pattern rule, and yes, it will work. But if I had an explicit pattern rule, I can say, well, the number of legs on 6 chairs would be 6 chairs times 4 legs each is 24. In other words, take the number of chairs and multiply it by 4. That's an explicit pattern rule. Both recursive and explicit are definitely valuable, and we use both of them. The last term I'm going to be defining for you today is common difference. The common difference is the difference between any two consecutive terms in a pattern. Consecutive means one after the other. So 3, 7, 11, and 15 are in an order. So from, in this case, 15 minus 11 is 4. 11 minus 7 is 4. The difference of 7 and 3, 7 minus 3 is 4. So we can see here that the common difference or pattern is add 4 every time. And we're now going to apply that to an example here. I have here a number of terms, a number of figures. So my first term has this blue polygon, has a perimeter of value 4. 1, 2, 3, 4. So my term number here has a perimeter of 4. I've indicated that already. I'm now going to start with this one. So our term value of 2, which is here, we're now going to count the perimeter starting from this side right here. 1, 2, 3, 4, 5, 6. So I have a perimeter of 6. Now I'm going to start counting this one. 1, 2, 3, 4, 5, 6, 7, 8. And that perimeter has a value of 8. For my term 4, I'm going to start here. See if you can predict this one before I count it. I'll give you a few seconds, without counting, of course. Let's try counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You may be able to notice a pattern by going down like this. We went from 4 to 6 to 8 to 10. So let's see if we can predict something here. Let's start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you predicted 12, you would be right. We're now going to find the common difference. That will be the difference between two consecutive or one after the other numbers. So the common difference of 6 and 4, it's 2. So we add 2 every time to get there from 4 to 6. Let's see if there's another one. 6 to 8 or 8 minus 6 is 2 again. 10 minus 8 is 2 again. 12 minus 10 is 2 again. At this point, we can decide, yes, we are continually adding 2 every time. So let's see what happens. Will it work? If we add 2, 12 plus 2 is 14. And my sixth term, if I made it, would indeed have a perimeter of 14. So I can keep adding 2 every time. And our pattern here, our pattern in this case, we are adding 2 every single time. We can also look for another type of pattern rule. Because I'm adding 2 every time, I can look at this question as saying, well, that's like repeated addition is multiplication. You learned many years ago that if you add a number over and over and over again, like 4 plus 4 plus 4, you added 4 3 times. So that's 3 times 4. Well, let's see what happens here. If I do all these 2's, it means I must be multiplying a 2 somewhere. So what if I did 1 times 2? 1 times 2 is 2. But I have a 4 here. 2 times 2 is 4, but I have a 6 here. 3 times 2 is 6, but I have an 8 here. If all I do is multiply it by 2, so 1 times 2, I will always be 2 short. So 1 times 2 equals 2. That's not 4. 2 times 2 equals 4. Well, that's not 6. 3 times 2 equals 6. But that's not 8. Every time we do this, we are short by 2. So how do you make up the difference? Well, you just add 2. So let's see if that works with this one. What is 4 times 2? That's 8. And add 2, that's 10. 5 times 2 is 10. Plus 2 is 12. 6 times 2 is 12. Plus 2 is 14. Let's see what would happen if we use that rule to find the 20th. I would say 20 times 2, that equals 40, but we know that's going to be too small by 2, so we're going to add 2. So 40 plus 2 is 42. And we could do this for any term, for our 25th term or our 60th term or our 100th term. We take our term number, multiply it by 2, and add 2 every time. And that is this section. Thanks, everyone. Have a good day.